but let's continue. Right, I was at the spot where I was talking about busting out the house. So, if, right, you are adding here, we're talking about adding numbers versus an arithmetic series. This time over here, I'm in a house. But you're adding values. So your sum is growing. So I'm adding the first term. I have one term of a sequence, then I have another term, but I'm adding the first term to the second term, adding. So I'm piling and piling and piling and piling and piling. But my values are getting so infinitesimally small, I will not bust out of the house. The values, every time you're adding something so small, it's almost immeasurable, and I won't be able to get above the ceiling. No busting out the house. Think of this as your bound, right? You will never go above that. So instead of diverging, which is growing without bound, you are growing, but you are growing to a bound, right? And you will never go above that. Kind of crazy. That's what convergent is. For reasons that you're not, and you won't know now, and you won't know even after calculus or differential equations, what you need to know is divergent series breaks our heart. Right? We can't deal with arithmetic, so we have nothing to do with series that don't converge, and our arithmetic series don't converge. They grow without bound. There's not a lot of math we can do with these applications. And again, these applications, we can do a few with like a bouncing ball, and the ball, you bounce a ball, and the heights of the bounces keep getting smaller and smaller, blah, 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 blah. That's all well, fine, and good. But true applications of these problems are in communications, right? It's engineering, computer science, all that kind of stuff. Your drones, your drone communications, your cell phones, your GPS, all of that takes convergent series. For now, all we can do is give people convergent series. We can just say, this one's no good at divergence, this one is good at converges. Further, what's awesome about geometric series that do converge is that if it does converge, I can actually find what that bound is. What is that sum to which, after I get to this sum, I get to this bound, and I will never, ever, ever go above it no matter how much I keep adding. So this formula should look a little familiar to you. And it comes from the partial sum, right? We talked about that weird partial sum. So like if I want to stop my geometric series after the 20th, let's say, I want to add all the first 20 terms. Remember, that is the the first term times 1 minus your common ratio to your 20 over 1 minus your common ratio. Well, remember, if we have a geometric series that converges, the common ratio is less than 1. So let's pretend our common ratio is a half. Let's pretend our first term is, 3. So 3 times this fraction, right? But think about what's happening to the numerator. As you get the 20th partial sum, so the sum of the first 20, you're making this a 20. But you're raising 1/2 to the 20th. Isn't 1/2 to the 20th a really, really small number? And let's suppose I wanted the 200th partial sum. What's happening to 1/2 to the 200th? Isn't this whole piece, as you go further and further to your partial sums to the 2000th, Isn't it true that this goes to a big fat 0? And what is 1 minus 0? 1. What is a sub 1 times 1? A sub 1, baby. So there really is a little infinity sign underneath here, but we don't put that. It's inappropriate because infinity is not a number, but that is the partial sums, the limit of the partial sums as the partial sums goes to infinity. Woot! So here is an exercise. We're going to work with these 3 examples, but I need to tell you that in your homework tonight, you will not be asked this first part. This is conceptual. We're going to try to build some conceptual knowledge here. This is what you're actually going to be asked to do in your homework. So I'm going to do the first problem, and I'm going to ignore the partial sum piece first. So if I want to know, does this infinite series converge? I hope it's geometric. Is it? 0.3, right? What is the common ratio between 0.03 and 0.3? Right? Isn't that the same as 3 over 100 divided by 3 over 10, which of course is 3 over 100 times 10 over 3, and the 3's cancel out, and I get 1/10. That's my common ratio. And is the absolute value of your common ratio less than 1? Yes. Therefore, you say this infinite series converges, which means the sum grows, but grows to a bound, and that infinite bound is a sub 1 over 1 minus r. And of course that is 3/10 times 1 over 1 minus 1/10, which is 3/10 times 1 over 9/10, which is 3/10 times 10 over 9, which is 1/3. So remember, we love convergence series. We don't know why exactly, but we love them. So we have a situation with the house. You are adding 0.3, adding 0.03, adding 0.003, adding. You keep adding, adding, and adding, and adding, and adding, but such infinitesimally small numbers that your sum is going to stay in the house. Ha! It's kind of ironic with quarantining, hey? So you're going to say, and further, you can tell me what your bound is. Your sum grows and grows and grows, but to a boundary of 1/3. Okay, bounded above by 1/3. Woot! Heart safe. Now I'm going to show you the concept behind that. Is that 1/3 comes from a limit of partial sums, which is kind of hard to think about. But what if I asked you for the first partial sum of this series? So I didn't, not infinite. That's 0.3 times my 1 minus r to the first over 1 minus r. Hopefully you can see that's 0.3. The next partial sum is the first term times 1 minus 0.1 over 1 minus 0.1, but the numerator's 0.1 is squared. Well, that is 0.33. The third partial sum is 0.3 times 1 minus 0.1 cubed over 1 minus 0.1. That's 0.333. And if you keep going, The limit of the sequence of partial sums is approaching 1/3. That's my bound. But if you look at the next one, does this series converge? Hopefully right away you can see this is not geometric. This is arithmetic. D is equal to 5. You say this is arithmetic. It diverges, and you're done for your homework tonight. Conceptually, why does it diverge? Well, the formula for a finite sum of an arithmetic sequence is n, which is 1, over 2, a sub 1 plus a sub n, which if you're only doing the first, right, and that's 10 times a half, which is 2, which is 5. S sub 2 is 2 over 2 plus the sum of the first two terms. S sub 3 is 3 over 2 times the sum of the first term and the third term. Which is 30. S sub 4 is 4 over 2, first term plus the fourth term, which is 50. If you notice this nice progression in the first problem, 0.3 to 0.33 to 0.333 to 0.33333, those numbers are approaching 1/3. What are these numbers approaching? The limit of 5, 15, 30, and 50. What is the limit of those numbers? Infinity. So the limit of the sequence of the partial sums is infinity. That's when you get diverge. Heartbroken. This next one really messes with kids. You might think it's arithmetic, but negative 1/3 minus 1/3 is negative 2/3, and 1/3 minus 1/3 is 0. Whoops. Is it geometric? Ooh, I'm starting to get my hopes up. This looks geometric. Negative 1/3 divided by 1/3 is negative 1. 1/3 divided by negative 1/3 is negative 1. Ooh, it is geometric, but what's true about my common ratio? The absolute value of my common ratio is greater than or equal to 1. This is going to bust out the house, and kids really can't grasp this situation, right? Because they're like, wait a second, if you keep adding those, it looks like I'm getting 0, Ms. Getz, right? But remember, it's the limit of the partial sums. So this is geometric. My first sum is 1/3 right? A sub 1 times 1 minus my common ratio to the first over 1 minus my common ratio. So what is this? This is 1 minus negative 1 to the first is negative 1, so that's 2 over 2, which is 1/3. But what is the next one? Well, negative 1 squared is 1. 1 minus 1 is 0, so this is 1 over, right? This is 0 over I don't care. This is 0, and 1/3 times 0 is 0. Well, what is the third? Can you see what's happening here? You've got a bounce situation. 1/3, 0, 1/3, 0 is the limit of the numbers, right? The limits of those sums. Limit of 0.3, 0.33, 0.3333, 0.33333. That limit is approaching a third. The limit of 5, 30, 5, 15, 30, and 50, that limit is infinity. What is this limit? A third, 0, a third, 0, a third, 0. That limit does not exist. You're not approaching anything. So kind of my bust out the house analogy doesn't really work, but that's why mathematically they don't talk about busting out the house. Mathematically they talk about whether the limit of the partial sums approaches a number, approaches infinity, or does not exist. And it is only when the limit of the sums approaches a number do you get converging, otherwise diverging. Let me show you a kind of a graphical analysis of this. So here's that negative 1/3, or sorry, 1/3, negative 1 to the x, right? That was that last series where a sub 1, right? The first was 1/3, and then our common ratio was negative 1. This is not the graph of the sum. This is just the graph of the terms. Look at what terms I get. Whoa. Look at that, right? So when you add those, the limit of the partial, right? When you add those terms, I know it really looks like you're adding to 0, but if it's the limit of the partial sums, one partial sum is a third, another partial sum is 0, so on and so forth. Versus, what if I change this to the first one? What if this is, right, this was 0.3, and this was 0.1. Look at that, right? Can you see the terms, right? That's very hard even for this graph to show. The terms are getting smaller and smaller and smaller, and as a matter of fact, they're so small they look like 0. So when you add, this is not the graph of the series, this is the graph of the terms. When the terms get so small and you add them all up, if you're geometric, those terms are so small, we can prove that the sum will never get to, not this horizontal asymptote at 0, but a horizontal asymptote where you're growing. Look at this one. This is negative 1 to the x over x. Look at those terms, though. That's kind of cool, isn't it? Can you see, though, that those terms, right, you've got bouncing, but you have this extra divided by x going on. Whee! I wonder what happens when you add all those up. Questions. All right, so this is more like what your homework is going to ask you. They're not going to ask you about those partial sums or anything like that. It is just going to ask you, if the series does converge, find the sum. So hopefully you're starting to realize that you really like when you're given summation notation, because you've got the rule or the pattern right there. And you recognize this is geometric. Further, you recognize that r is equal to 1/2 and that the absolute value of 1/2 is less than 1. Therefore, you're going to converge. And since you converge, you can tell me you are going to stay in the house, and that the bound, the upper bound for that sum, is your first term times 1 over 1 minus r. So you're going to go and find your first term. Be careful, right? Read k is equal to 1, so you're going to put 1 here. 1 minus 1 is 0. 1/2 to the 0 is 0. So my first term is 2 times 1. 1/2 to the 0 is 1, and 2 times 1 is 2. And my common ratio here is 1/2. So this is 2 over 1/2, which is 4. Right? So you're going to stay in the house. Your sum stays in the house. Further, you can tell me that the bound on the house, your upper bound, is 4. So you're going to add 2 times 1/2 to the 0, 2 times 1/2 to the first, 2 times 1/2 to the second, 2 times 1/2, but the numbers are going to get so infinitesimally small, you will stay in the house. And further, the height of the house is 4. Graphically, you think the terms decrease like this, but the sum increases. The sum increases, but it increases to a horizontal asymptote of 4. This is the top of the house. Will never, ever, ever, no matter how far you're adding numbers infinitely, that's kind of crazy. Maybe you can kind of see right away that the second one, right? The second one breaks our heart. Heartbroken, right? Yes, I've got the rule right here. I can very quickly see it's geometric. I can see my common ratio is equal to 3/2, but the absolute value of my common ratio is greater than or equal to 1. Therefore, I diverge, and I want nothing more to do with you. You diverge, I'm done. How about the next one? Heart saved, right? Geometric. Summation, so I've got the rule. It's geometric. R is equal to negative 0.3. And the absolute value of negative 0.3 is less than 1. So I converge, and I can go on and tell you that the infinite sum is the first term times 1 over 1 minus r. Be careful here. Since r is negative, this is negative 0.3, and my first term is, so my index starts at 0, so put 0 there. Negative 0.3 to the 0 power is 1. 4 times 1 is 4. So this is 4 over 1 plus 1.3, which is, please don't leave your answer that way. Okay. Sometimes you can't avoid leaving the fraction, the decimal, that's fine, but certainly no decimals within fractions or fractions within fractions, and when you can, please do express your answer as a fraction. So this one's kind of annoying, right? I could kind of see right away, oh, this is geometric and r is good to go. Oh, this is geometric and r is good to go. Oh, this is geometric, but r is not good to go. Here, I have to see if it's arithmetic or geometric first. This is geometric, right? 1/3 divided by 1 is 1/3. 1/9 divided by 1/3 is 1/3. So this is geometric. My common ratio is 3/2. Is 1/3. The absolute value of 1/3 is less than 1. Therefore, I do converge. Heart is safe. And if I converge, my infinite sum is first term is staring at me, right? 1, 1/3, and of course this is 1 over 2/3. which is 3/2. Yay. So that's what your homework, that's what the majority of your book problems are like. And the last, so let's recap that before I give you the last couple of problems. Our strategy so far, does the series converge? First thing you want to look at is if it's arithmetic. If it's arithmetic, here's what I want you to write. Here's what I want to see on your homework. Arithmetic breaks my heart. I want you to show me that you found what your common difference is. Then I want you to say, tell me that that means it's arithmetic. And then from there, you can just say it diverges and be done. Right? We don't care about you anymore. It's a divergent series. However, if you look at your series and it's geometric, and then you test your R, so you say, oh, it is geometric, but I tested my, you test your ratio and it's greater than 1. You also, so you tell me it's geometric, tell me that you tested R and what you got, and therefore you can say diverge and you're done. And you're done. But if you test and it's geometric, and you test your common ratio and it is less than 1, you say I converge, but then you also give me the sum. Okay? So that's our strategy. Now, the last two, I think, problems of your homework do this one application of series. Now, I have to say it's not that useful. Please don't stress too much about this. As a matter of fact, in AAF, when we did the 18-wheel song, I gave you a handout from IB, and it showed you another way to take a repeating fraction, which is rational, right? This is a rational number. And of course, a rational number means you can represent it with a ratio of integers. So here's how I want you to do the last two problems. So I want you to write 5.171717 as 5 plus 0.171717, repeating. Then I want you to say, well, that's actually 5 plus 17 plus that's fine. Plus 17 over a lot of ones, right? Then I want you to, so this is step 1. Step 2, I want you to take this last part here and talk to me about it representing it as a geometric series. So I want you to take 17 over and show me what your common ratio is, which of course is actually times 100 over 17. Cross out the 17s, cross out 2 of the zeros, and you end up with 1 over 100. So then I want you to write this as 5 plus the infinite sum of that geometric series, since the absolute value of the common ratio is less than 1. So that's 17 over 100 is my first term, times 1 over 1 minus my common ratio. Right, 100 minus 100, right? And that, of course, is actually 5 plus 17 over 100 times 100 over 99. If I change 5 into a denominator with 99, you're going to get a 512 over 99, and go ahead and put that in your calculator and look at the decimal you get. Now your calculator is going to round the last digit because that's all it knows how to do, but OMG. Again, please don't stress too much about this. Practice it a couple of times, right? But the most, so it's nice to see, just another way to practice working with series. But that first slide before was your real series work, infinite series work. So try those homework problems. Don't let this stress you out. This is hard and weird and unusual and crazy and blah, 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 blah. But you'll be all right, I swear. I'll take you through it. Hang with me. All right, I will see you next time.